Hi everyone, this is our second lecture on work and power. In particular, we're going to be talking about bicycles today. So let's get started. In order to get started, we are going to take a look at a relatively straightforward fact. To get to the top of a hill, when you're biking, you're increasing the potential energy of the bike, right? Because the bike, as you go further and further up, wants to roll back down the hill. And you're doing that by converting the kinetic energy of your legs into potential energy. So just like when we talked about previously mousetrap cars, where does the energy come from? How do we get that kinetic energy to potential energy? Well, the answer is we apply force on our pedal along the distance of our pedal stroke. And we call this force times distance. We call this quantity work. And work is equal to change in the energy of an object. And so we think of our system, in this case, a person on a bicycle going up a hill. At the very bottom of the hill, he has 0 joules of stored energy, 0 joules of potential energy. And at the very top of the hill, as he works his way up, more and more of that, he's putting in more and more work, and he's getting more and more potential energy, until he's at the very top, and he has 1,000 joules of potential energy. Okay, before we go any further, let's do a couple of quick practice problems so we're on the exact same page with this work concept. Work is equal to change in energy. Question 1. You ride a bike up a hill. At the top of the hill, the bike has a total of 500 joules of energy. What type of energy does the bike have, provided it's come to a stop at the top of the hill? All right, well, at the very top of the hill, it's not moving, so there's no kinetic energy, not moving. In this case then, because mechanical energy is equal to potential energy plus kinetic energy, if we have no kinetic energy, we're at a complete stop, all of our energy must be, therefore, potential energy. Okay, so our potential energy, in particular, is gravitational potential energy, and that's equal to our 500 joules. Not too bad. Question 2. How did the biker get 500 joules of potential energy? AKA, how did she get to the top of the hill? Well, the biker, like any biker, pedals. And by pedaling, does work equals force times distance equals change in energy. All right, so we're applying a force across the distance of our swing to get more kinetic energy, and that's being converted into potential energy, until at the very top we have only potential energy. All right, question 3, Matt applies 100 newtons of force over a vertical distance to get to the top of the hill, 100 meters tall. How much work did he do? Well, work is force times distance, so we just have 100 newtons times the distance of 100 meters, and we get, let's find out, 100 times 100, okay, 100 times 100, and we get 10,000 newtons, or 10,000 joules, excuse me. All right, this is a lot of energy. Matt definitely wants to slide back down the hill, and he'll go quite fast at the end. Okay, so we got to the top of the hill, and if you're anything like the people in my family, we like to use gears. I remember when I was younger, my mom would always say, like, you're using the gears, that's cheating, right? You should stay in one fixed gear. That's not true. We like to take advantage of, our devices. So being able to shift gears is really important. And to understand that, let's go back to our idea that at the bottom of our hill, our potential energy is 0 joules, and at the top of our hill, our potential energy is 1,000 joules. So regardless of if you're in high gear, the physically large gear, or excuse me, low gear, or if you're in high gear, the physically small gear, regardless of what setting you're in, the change in energy to get from the bottom of the hill to the top is going to be the same. Okay. In fact, we'd say the work required to get to the top of the hill is going to be set by the mass and the hill's height, but that overall change in energy is going to be fixed. So we'd say work equals force times distance equals, in this case, 1,000 joules. All right, and so say you have a hypothetical race. You're going uphill, so is your friend, and you decide you're going to go in low gear, your friend's going to go in high gear. Let's see what happens. So we say the equation's the same. Work equals force times distance equals change in energy, 1,000 joules. So we'll write that out twice. Okay, you're in low gear. Low gear, we said, is the physically larger gear. So to get our pedal to go one complete revolution, because we're on our lower gear with a larger distance, we actually have to pedal more. So when you're in low gear, because we're using our larger gear, the distance increases. Okay, and since force times distance gives us our 1,000 joules, and this term is set, and we've just increased distance, that means that our force is going to go down. So our low gear uses a big distance, and because it's got a big distance, it's actually going to decrease the amount of force you need to get the same change in energy. And so low gear is the easy pedaling gear. All right, we still don't know if we win this race, but we know that we pedal less, or we pedal with less force. And this can be really good because our legs won't get as tired, right? Slow and steady wins the race. In fact, low gear is what we consider to be good advice for going up a hill. If you're going up a hill, you should be in low gear because it will require less force and your legs don't get tired and you don't suddenly start rolling back down the hill, which is quite unfortunate, right? Your friend who's in high gear is using the physically small gear, right? And so with the physically small gear, the distance becomes really small, and he's pedaling less. But because distance is small and we have the same change in energy, the force becomes really big. It's hard to pedal in the small gear. It's really tough. Okay, and so when would high gear be good? When you want to have to pedal less, you want to apply great force over a short distance, you want to change your energy quickly, right? Which we describe as high power. All right, one last thing. Say you want to get one more leg up on your friend, you want to beat him to the top of the hill, and you decide that from your experience in biking, standing up would be a really good idea. Why do people stand up on their bike? How does that actually help? Well, think about it from the forces involved, right? We said that the total change in energy, the total work required is set by the mass and the height of the hill. So this is our fixed term, okay? But this is the fixed term right here. You can, if you stand on your bike, you're increasing the force on your pedals, right? You're increasing the force, you're using your weight. And since the right side of the equation is fixed, force is going up. To get the same value, distance must go down. So if you stand on your bike pedals, you have to pedal less to get to the same top of the hill, okay? So let's go back to the question of who would actually win if you were talking about low gear versus high gear. Let's take a look. Power can give us this answer because power is change in energy over time. So let's think of it maybe in this case as, you want to go as fast as possible, so we could say changing kinetic energy. But if we stick with our hill analogy, we'll say that we end up with our certain potential energy, All right, and for both of you, this is going to be exactly the same. At the bottom, you have 0 joules of potential energy. And for you in low gear, it's going to take you 60 seconds to get to the top of the hill. And in high gear, it takes your friend only 10 seconds to get to the top of the hill. And you're like, okay, well, Mr. Mellor, there's the answer right there. Our friend won. Okay, but we're trying to generalize this. High gear is high power. When would that be good? So let's do a quick calculation. Power is work over time. All right, in this case, we have work is force times distance. And we are going upwards, right? So we're going against the force of gravity. So our force of gravity is m times the acceleration of gravity. And then we still have that distance term divided by time. So we get 70 kilograms times 10 meters per second squared times our distance of 100 meters divided by 60 seconds. All right, and know from experience this is going to give us 1,166 joules per second, otherwise known as watts. Okay, for our high power scenario, we have same thing, force times distance over time, change in energy over time. We have 70 kilograms, because our friend weighs the exact same amount, 100-meter hill, divided by 10 seconds. And this is equal to 7,000 watts. Okay, and so we can see that when you are in low gear, you have less power. When you're in high gear, you have more power. And so we said, going uphill, it's good to be in low power mode, such that the force required is smaller, force goes down. But if you wanted to say you were racing on a flat surface, if you wanted to change your energy as quickly as possible, get to a higher kinetic energy as quickly as possible, you would want to be in high power mode. Okay, so when do we use each gear? For hills, use low gear. For downhills or flat surfaces, you want to use high gear to get the fastest possible change in energy. Low gear is low power, saves your legs. High gear is high power. You get a change in energy very quickly. All right, we have one quick practice time. We're just about done. You get to the top of the hill doing 100 joules of work over 10 seconds. How much power do you use? Okay, power is work over time, change in energy over time. 100 joules divided by 10 seconds. Not too bad. We have 10 watts. Question 2, you get to the top of the hill by doing 100 joules work over 10 seconds. Your best friend also does 100 joules work to get to the top of the same hill. She gets there in 5 seconds. Who has more power? Okay, P equals W over T. We have 100 joules over 10 seconds. B equals W over T, change in energy over time, 100 joules over 5 seconds. All right, we'll let you finish that, but our answer is, of course, in watts. Okay, and so we have been dealing with bicycles really as a segue into our next topic, which is levers and pulleys. But a bicycle is a version of a machine, in particular a simple machine, which are just devices that take advantage of this idea that work equals force times distance equals change in energy. And if you can manipulate the distances involved over which you apply your force, then you can manipulate how much force is required. And this is actually an incredible thing. We have our ancient Greek philosophers who say, give me a long enough lever and I can lift the world. The work energy theorem is insanely powerful, very useful. All right, we'll see you guys next time. Adios.